Hello everyone, my name is Tatiana Bohodorova. I would like to present a paper, Automated Design of Realistic Contingencies for Big Data Generation. This research proposes an algorithm for big data generation based on realistic selection of a set of contingencies for a system described by a undirected graph. The motivation behind the research is to generate enough data that contain contingencies. This data is meant to be used to train and test machine learning methods. Thus, the idea of this research is to generate trajectories of power system signals, magnitudes of current and voltage, angles of current and voltage under contingency, but only for those cases where connectedness of the network is preserved. The proposed algorithm for big data generation implies derivation and usage of realistic probability mass functions and graph theory to check validity of the resulted network after contingency. Thus, the algorithms start from sampling of type, location, and duration of the fault, following with the sampling number of outages and choose which one is going to be simulated first. The type of fault follows probabilities that are presented in the EPRI technical report. Duration of fault is sampled from the gamma distribution of fault clearing time. This distribution was derived from the following facts. A typical value of a fault clearing time is 5 cycles of a 60 Hz sine wave, while the shortest fault clearing time is about 3 cycles. The maximum time that a circuit breaker can remain closed under the short time withstand current is 30 cycles or half a second. For more details, refer to the reference 6 in the paper. For a generator, the fault location is said to be at the terminal bus. For a transformer, the fault is uniformly selected among its terminal buses. For transmission lines, the location of the fault within the length of a line is sampled using a uniform distribution. The number of elements that are tripped follows a geometric distribution function that is identified from historical data based on frequency of outages depending on number of elements. Sampling the first outage is done uniformly. After the first step, the algorithm performs check if there is one or more elements in the contingency. If k equal to 1, the algorithm proceeds with verification of integrity and presence of generation. If k more than 1, the steps 3 and 4 are performed before the verification. The presence of generation and integrity of the system are verified using a multi-graph representation of a power grid. The generation is present in the resulting graph if the trace, the sum of elements on the main diagonal of an adjacency matrix is bigger than 0. The integrity of the system is defined by the analysis of the graph's connectedness. The connectedness of a graph is verified by analysis of the Laplacian matrix, the number of 0 eigenvalues in the Laplacian matrix. L shows the number of subgraphs, islands of a multigraph. We're interested in those contingencies that preserve the integrity of this system. So at step 3 of the algorithm, a distance between elements of a multi-event contingency follows a geometric distribution, which is parameterized by identifying a ratio between probabilities of 2 consecutive values of distances between elements of a contingency. For example, for this graph, the distance between locations of outage 1 and outage 2 drops with the growth of a distance from the place of first element of contingency, which corresponds to reality. Thus, to conclude, the proposed systematic approach for contingency design allows to generate a large number of unique realistic contingencies, which can be used to train machine learning models for power system security assessment. Thank you for your attention.